Uh, so the reason I haven't pulled out yet is because I just wanted to make sure that I give you some notice as to when I will take them out. And as I said last time, form groups of 2 or 3, and assignments will be made on like a first come first serve basis because I would like at most 3 groups per paper. Okay, so for this reason, give a list of at least 5 topics in decreasing order of preference. Okay, so when you send an email, send the email to the TA group so that we know who sent what order and stuff. And yeah, I just have a tentative subject, but you can have anything. But make sure you include make sure you send only one email per group and include all the names and UIDs of the student. So this is the main thing about the project, and also list at least 5 topics because some of them will run out soon. Okay, so I don't know, for some reason some topics are more popular than others. It happens every year. So just give a list of around 5 topics. Okay, so any questions on this? Okay, and hopefully you guys have thought a little bit about forming groups. So yeah, form groups of 2 or 3. Oh, another thing I forgot is that sometime so it's maybe 3 weeks from now. Okay, so we'll have one-on-one meetings. Proposal. Okay, so you'll have to come up with a short proposal about what you plan to do in about 3 weeks' time. Okay, so that way you'll have about a month to actually do the stuff. And I will usually meet every group. Okay, so I'll have a per paper meeting. So everybody who's working on one paper, I'll meet at one time so that they can actually do different things about the same paper. Okay. So this will happen about 3 weeks from now. I'll send a schedule once that approaches. But make sure you go through the papers and you have a sense of what you want to do in about 3 weeks. Okay, so that's that. So this is tentatively end of. Okay, so this is last week of October. Okay, so any questions on this? Alright, so yeah, this is straightforward. Most classes do it this way. Alright, so what did we start doing last time? So last time we started looking at probabilistic algorithms. Okay, and we came up, and the general idea here is randomness can help in designing efficient algorithms. Okay, so that's the general idea. And we saw a few examples of this, a few non-trivial examples. So I just wanted to illustrate the power of these kind of methods. And we saw one example is called polynomial identity testing. And here we wanted to test if 2 high-degree polynomials were equal. And we said that a very powerful way of doing it is to check if they are equal at random points. Sounds like a stupid test, but it works really well. And the reason is that in general, the difference has a small number of roots. Okay, so that's the reason this test works. Okay, and I also said that there are simple probabilistic tests that check if a number is prime or not. Okay. So I didn't explain why that test works, but I just roughly mentioned what it is. Alright, so what is the goal for today? So today we want to. So these were some interesting examples that I thought would just highlight the power of randomness. So today we'll start thinking about how you actually reason about probabilistic algorithms. Okay. And the first kind of questions we will look at are, in some sense, I think of it as you use randomness to show that some bad events that rarely happen don't happen. Okay, so So that's what I mean by randomness can avoid unlucky choices. Okay. So this is, we'll illustrate this with the use of quicksort and hashing. Okay, so maybe some of you have seen these examples before. At least hashing, many of you must be familiar with, right? Because you hash with some probabilistic function, and unless you're unlucky, things spread out pretty evenly. Okay, so that's what we want to formally analyze. Okay, and so what a mathematical tool that will come up often is this notion of expectation, and there is this notion of linearity of expectation. It sounds like a very simple thing, but it implies it implies powerful things. So we'll see some examples of that today. So that's the plan. Alright, so let's start. So I wanted to start with the toy example we saw last class. Okay, so you have an array, and I tell you that n by 2 elements are promised to be 0. Right, and this is the algorithm we saw last time, and your goal is to find one index I such that a of I is 0. We said there's a very simple algorithm for this. At each step, randomly pick an index, check if a of I is 0, if so, return that index. Okay. Otherwise, just repeat. And this is an example of an algorithm, of what I call Las Vegas algorithms. Okay, so this has the property that it is never wrong. That's maybe not what you associate with Las Vegas, but yeah, so this is, it has the property that it's never wrong. Okay, and secondly, it may or may not terminate. Okay, so the resources, the time, the running time is can be large if we are unlucky. And what we said last time is that the probability that the running time is more than t, that algorithm has the running time t is at most 1 divided by 2 to the t. So this is a very simple calculation that we saw last time, because we said that remember there was also a question about why is it at most, why is it not exactly 1 by 2 to the t, and we said that we are only promised that half or more are 0. So maybe more can be 0. And so this is the kind of guarantees that typically show up with Las Vegas algorithm, okay, where the running time could be large, but they're small with pretty high probability. Okay? So if you want the running time to be less than or equal to t, then it's true with probability at least 1 minus 1 by 2. So that's so this is typical. This is one way of thinking about such algorithms. And in general, yeah.
So when you say that it can be wrong, that's only for randomized algorithm. That an algorithm can be wrong.
Yeah, so in this case, the algorithm is never wrong, right? Because if it outputs an index, it's always some number which is for which a of I is 0. Okay? But there could be other algorithms. Yeah, I mean, you could imagine a trivial truncation of this algorithm where you say that check for some k steps, and if you find some I such that a of I is 0, return it. Otherwise, you just output a random index.
That wouldn't be a Las Vegas.
That would not be called a Las Vegas algorithm. That is called what I call Monte Carlo algorithm. Okay, where you can be wrong, but you always have a bounded time, right? Okay. Yeah. So this is just a subtle technical difference. Usually, you can go between the two. Okay, so you can spend more time and always pick right with higher probability. So yeah. In fact, I'll just mention that. Okay. Yeah. So all right. So this was one simple example, but typically, what we'll be interested in is what will happen is that running times can vary, okay? And what we care about will usually be this quantity called expected running time. Okay. So this is a mathematical definition. So you think of the running time as a random variable. Is a random variable. Okay, actually, yeah, can someone define a random variable? So, I'm sure most of you have heard it in some probability class or machine learning class. Yeah.
It's a function that assign a probability to every event, and they should add up all.
Yeah, so that's a probability measure. So a random variable is just some random quantity. Okay, so it's it's some parameter of the algorithm or parameter that you can define that depends on the choice of the random bits we've made. Okay, so in this case, the running time, the running time depends on the choice of the random bits that we've made, right? Like you got a bunch of random indices, the choice of that determines the running time. So the running time is what we call a random variable. So, and typically, and this is a real valued random variable in the sense that it always takes non-negative values. So the running time depends on the coin tosses so far. Okay, that is, by coin tosses I broadly mean with the random choices that we've made so far. Okay? So they may not literally be some coin tosses. So that's the mathematical notion of a random variable. And so for every real valued random variable, you can define what is called an expected value. Okay. This again, hopefully many of you have seen in your probability class, but I will define it a little bit later in this lecture. Okay. So you can define the expectation of any real value random. Expected value. We'll define it. Okay. So intuitively, it is what you would expect. Okay. So the expected value is the amount of time you expect the random variable to take. Okay. And this is something you guys. I guess there was a question on homework 0 also, where I told you, okay, so suppose you keep tossing coins, or let's say, I don't know if it was dice or coins, but you throw a dice multiple times. What is the expected number of times you've got to throw this dice so that you see a 6? So what would be the answer here? Yeah, it's 6 times, and in this case, you can do it without any calculation. I mean, but formally you can say it is for every k you have some probability that it's k, and you sum this overall k going from 1 through. Okay, so. So yeah, I'll define this in a little while. So I just wanted to mention that this is just a very standard quantity, and it corresponds to intuitively what you think of as the expected number of times. Okay, all right. And the other thing we'll discuss when talking about randomized algorithms is the success probability. Okay, so as I said, some algorithms always produce the right answer, some algorithms don't, and in which case you want to reason about with what probability it produces the right answer. Okay. And the other thing I wanted to mention is that there is a pretty general Very simple trade-off between these two. So if I have an algorithm, like say I have an algorithm, we have that has success probability equal to 1/2 and running time equal to t. Okay. And here I am assuming that the running time is actually a deterministic quantity. This itself could be a random variable, but my simple statement is not going to consider that case. Okay. So let's think of, for example, in this trivial example, suppose I just repeat this for capital T steps. Okay. So this would have certain success probability and it would have a certain running time. Then I want to say that then there is that has success probability whatever large number you want. Let's call it 99 by 100 and running time. That's roughly t. Okay, so it's actually let's be a little bit more formal. So I want to increase the success probability to say 1 minus delta. For delta it's pretty small. And it has a running time that is t log 1 by delta. Because I wanted to show the dependence that it's only a log dependence. So I can boost the success probability to like a pretty tiny quantity. Okay? So that's why I didn't have a numeric example. Alright, so I claim this. Okay, so anyone see why this would be true? I have to make one small assumption, but I'm waiting for somebody to say something before I mention that. Because, like in going back to the previous example, right? Like if I had an algorithm where I wanted to find an index such that AFI is 0. Yeah. Yeah. So this is the assumption that I was going to mention. Okay. So this is a great point. So what he's saying is. If you are right, how do you know you are right? Right. So one thing you have to assume is that we can check. Yeah. So we can test if we have succeeded. Okay. So for optimization problems, usually, so you can't really test this thing, but you do the same thing, but you take the minimum of what you get or something. Okay, but first let's prove this very simple claim in the case when you can actually test if we have succeeded. So how would you do this? I give you a bit more time, but I want you to be more confident of succeeding. Anybody else? Okay.
In this example, we could just check 2 points instead of just checking 1 to double our success probability, but double our runtime. And so in the general case, you could imagine just check more things, see if they're successful. That would improve our chance of being successful.
Right. So the high-level thing that he's mentioning is that in some sense, suppose you run this algorithm twice. So the first time it succeeds with probability half. Probability half it fails. And the second time, maybe it succeeds again independently. Run it completely independently a second time. And second time again it succeeds with probability half. But the probability that you failed both times is half times half. Right? So, and even if you succeeded in one of them, because we can test that we have succeeded, you can just return whichever instance succeeded. So this is a very simple argument. So, and you can extend this to multiple rounds as well. So the simple strategy is pick. So in general, you have to repeat something like log 1 by delta time if you want the success probability of 1 minus delta. So pick r equals log 1 by delta just for clarity. And now repeat r times run if it succeeds, output answer. Okay, and if not, you just repeat. Okay, and you stop when you succeed. And now the failure probability of this new algorithm. So this is alg prime. Failure probability. Alg prime is now less than or equal to 1 by 2 to the r, because each of these repetitions you succeed with probability half, so failure probability is less than or equal to. And these runs are all independent. Okay, and this is equal to that. Okay, so this is so this is just a very simple repetition act. And you can often do this for optimization problems where you don't actually know if you can test if we succeeded. But what you do is you typically, suppose your goal is to solve some minimization problem. You run the algorithm multiple times, you get a bunch of answers and you take the least of them. Okay? And if one of them was guaranteed to output the true minimum with probability at least half, then you would get the true minimum with probability at least 1 minus half. So this is the setting in which you would apply this to optimization problems as well. Okay, but generally, for many problems, you can test if you have succeeded pretty quickly. So that's why it's this is not it's pretty good enough thing to work. All right. So let's so given this, so let's now see a simple example of another popular randomized algorithm. Okay, so let's do a quick flashback into sorting. Okay, so again, you have an unsorted array, you want to sort it, right? So the most simple sorting problem. And consider this the following algorithm. This is called quicksort. Okay. And what you do is you pick the first element as a pivot. It's called a pivot because you A0, A1, so on, n minus 1. This is your unsorted array. You pick this element which you call the pivot. And now you go through the whole array, divide it into two groups. Things that are less than this pivot and things that are bigger than this pivot. And let's call these arrays B and C. This is what we used before. So B is the array which is things less than or equal to A of 0. Or element. Let me be a bit more. That are less than or equal to A of 0. And C is the same thing. The bigger than. For a moment, assume that all the numbers in A are all distinct. Okay? It doesn't really matter. So now, so now you have these two different arrays, and you sort them recursively, and now you append the sorted version of B, you append A0, and then you append the sorted version of C. So this is a simple divide and conquer type algorithm, except that you divide it based on this pivot. Okay. So that's what we did. Alright, so now what is the running time of this algorithm as is? Yeah?
We go up in square.
Yeah, sure, it's always, yeah, so this one, the running time is O n squared, and why do you say it's O n squared?
Just because I remember from introduction algorithms and dash numbers.
Good enough, yeah. So, that is true. I mean, and you can also prove this very easily because, you know, you're always, each of B and C has a size that is, that's at most n minus 1, right? And the sum of their sizes is actually equal to n minus 1. So, yeah, so the size of these two, neither of them will contain a of 0. So for this reason, the sum of their sizes is n minus 1. And so you want to solve a problem of size n, you are recursing onto two subproblems, the sum of whose size is less than or equal to n minus 1. So your recurrence will always look like t of n, and this is equal to t of some a plus t of b plus o of n, where a plus b equals n minus 1. And you can show that for any recurrence like this, you can bound this by n squared. Okay, so the worst case will actually happen when a equals n minus 1 and b equals 0. Okay, so the worst case. Okay, so this can be shown by induction. Okay, and as he said, you've all seen it in introductory algorithm, so let's not spend too much time. Okay, so this is, but the point to note is that in the worst case, you have a being n minus 1 and b being 0, right? So in some sense, we are saying that for this, when this running time is O of n squared, okay, then one of these one of B and C has size n minus 1, the other has size 0. Okay. And that is the setting in which we get this running time of n squared. Okay, so let's go to this slide. So the question we are asking is, when is the running time roughly, let's say n squared by 2 or something. Right, so when is it quadratic? Okay. And I want to argue that for this algorithm to have something quadratic, you must really have this kind of a lopsided B and C. Okay, so one example in which this happens is B has size n minus 1 and C has size 0. Okay, so if you had a scenario like this, then your recurrence would end up being T of n equals T of n minus 1 plus T of 0 is 0, so I'm ignoring that, plus O of n. And this one adds up to something like n. Okay. But now the point is to know that this is roughly the only case, these are kind of the only cases in which this recurrence can be pretty bad. Okay. So if you somehow ended up with A and B both being bigger than n by 3. Okay, so each of these numbers, so sorry, maybe I should call them, yeah, okay, I've called them A and B, so that's fine. Okay, so A and B are the sizes of B and C respectively. Okay. So these are the sizes of these things, and let's say both are at least n by 3. Then the most lopsided recurrence you can get is something like T of n equals T of 2n by 3 plus T of n by 3 plus 4n. Okay. And this one you can show actually solves to n log n. Okay. So this the simple exercise for you. This solves to O of n log n. Okay. So in some sense, what's going on here is that if your A0 split your is kind of in the middle of the sorted array. Okay. So this is what we call the approximate median in this other median finding algorithm we saw, right? So if your A of 0 is somewhat in the middle of the ideal sorted array, then this algorithm runs really quickly. Okay, it only runs in time n log n, which is comparable to merge sort and stuff like this. So is this point clear? So if A of 0 is almost in the middle, of the sorted version of K, then the algorithm does well. So note that this is there's a caveat here, right? The caveat here is that this should always keep happening. Right? I mean, it can't just maybe you were lucky and maybe A of 0 was actually exactly in the middle, but maybe next step onwards things you did not have this condition. So that's also very bad. And what you want is this should keep happening. So now the question is, how do you ensure that something like this keeps happening? Okay. And so this is the idea behind the quicksort algorithm. And the main idea is, instead of picking A of 0 as a pivot, choose a random array element as a pivot. It's a very simple idea. So the main idea is, instead of picking A0 as a pivot, pick a random. Pick some random index I and pick A of I as the pivot. Alright? And now let's say we ask, what is the probability of a lopsided partition? Okay, what do I mean by lopsided partition? What is the probability that the min of A and B is less than n by 3? We said that if both A and B were little a, little b were bigger than or equal to n by 3, you get a pretty decent recurrence. Right? And so this is how we define lopsidedness. Okay, so now you ask, what is the probability that you get a lopsided partition? Yeah, so he's saying that this probability is smaller than or equal to 2. Okay, maybe it's in this case exactly 2. Let's say exactly 2 by 3. And why is this?
One chosen in the middle part,
Then
then it's good.
okay.
Otherwise,
yeah, so I guess what he's saying is pictorially, let's now imagine drawing these AIs on the line, right? So I said AIs were all distinct. So A0 is somewhere, A1 is here, A2 is maybe here, A3 is here, so on. But you have n such points on the line. These are all real numbers, they're all on the real line. Now the point is, if you pick one of, divide this into like n by 3 groups by n by 3. If you've picked a number here, then there's no way you get a lopsided partition, right? Because this number has more than n by 3 things less than it and more than n by 3 things bigger than it. So the only way you get a lopsided partition is if you pick somebody here or somebody here. Okay? And this is the main idea. Okay? So in this case, the probability that you picked a lopsided element is equal to actually 2. Okay? Because yeah, so this is exactly the probability that you pick somebody in these two sides. So it's exactly equal to 2. Yeah.
So it will be 2 times n over 3 divided by n.
Yeah, right. Yeah, so you're uniformly picking one of these n things, and these two are like, these two end up in lopsided, and this one ends up in a no lopsided. So with probability at least a third, you can be lucky. Okay, so that's what this thing is. Okay. And usually, yeah, and this, it turns out, is good enough to yield an overall good algorithm. Okay, so we'll see why that is so in a little while. But is the idea clear? So the probability of succeeding, and in this case it means like no lopsided partition, is at least a third. So there's a decent probability that you produce, and like the next instances that you produce are not lopsided. Okay. All right. So now we want to show that this implies that the expected running time is small. Yeah. Yes. In this case, it's equal to 1. Right. Yeah, in this case, it's exactly equal to 1. Alright, so any other comments? Alright, so now we want to show that this algorithm already has a good expected running time. So we want to show that the algorithm has a good. Okay? So, but is the algorithm itself clear? Each time you pick a random element of your array and you pivot around that, you partition the whole array into things less than this random element, things more than this random, and you just recurse. And the idea is that most of the time, or at least with a decent probability, you will reduce the size of these recursive calls by a fair amount. And you can think about this now more formally, right? So suppose I picked 10 different pivots. Okay? To get an intuitive sense as to why this always works pretty well, suppose I picked, I'm in depth 10 of this recursion. Now you could argue, what is the probability that none of these divisions were actually like succeeding? The probability of one thing failing is like 2/3. Probability that all of them failed is like 2/3 to the power of 10, which if you compute is like a really, really tiny quantity. Okay? So this is intuitively the reason why, even though your success probability doesn't seem too high out here, it is still good enough. So, alright. So that's what we will call CC. Okay, so let's because I need to formally define the expectation and so on. So this is what we will analyze. Okay, so we want to say the term that I want to show is that the expected running time of Quicksort is O of n. And I will define what I mean by expectation. Okay, so this is, let's go to a quick detour about random variables and expectations. So we'll only talk in this, in what we'll see at least, about real valued random variables. Okay, so random variables, think of it as x. Usually we denote the random variables by capital letters. So this is x. It takes values and it depends. It takes the values that depend on the choices of that. And this is something you define. Okay. So right now I'm defining the random variable to be the running time of this procedure. Right? So note that the running time of this procedure is not fixed. It depends on which element we chose as the pivot. Okay, if we were unlucky and chose like a corner element as a pivot each time, then the running time would be very long. Okay. So in this case the random variable is the, but in general you can define random variables anyway. So it's just it depends on that analysis. Alright, so that's just a random variable. What is the expectation of a random variable? We will write this as E of x. E of x is usually defined as an integral, but let me just write it as a summation. Okay, summation over, let's say it only takes integer values. So it becomes simpler. Then it's sum over all integers I, the I times probability that this random variable is equal to. Okay, so this random variable takes various integral values, and each one happens with some probability, and this is how you define the expectation. Okay. So you take the probabilities weighted by the I. So let's just take some very simple examples. Okay, so if you had a random variable x that denotes the outcome of a coin toss, it is 0 if coin is heads, 1 if coin is tails. This is a fair coin, let's say. So what is the expected value of this random variable? So this is a random variable that takes only 0 and 1 values, right? It does not take any other values. That's how I defined it.
1.5.
So yeah, so it's 0 with probability half, 1 with probability. So what you would do is 0 times a half plus 1 times a, which is 1. Okay. And similarly, you could define the random variable x which is the output of a die. Right? So it is 1, 2, 3, 6, depending output of die. I don't know if they call it a die or a dice. One of them is single. I think a dice. All right. So you have you have this. Right? So in this case, what is the expected value? Yeah. So here it is 1 times 1/6 plus 2 times 1/6 plus so on. So this turns out to be 6 times 7 times 6 by 2. So if you sum 1 plus 2 up to 6, you get 7 times 6. So this one is 3.5. So note that the expected value often does not correspond to any of these outcomes, right? So there it's half, here it's 3.5. So in some sense, this is the average of the random variable chosen appropriately. It's a glorified average. Okay, so the expectation is some kind of a glorified average. Okay? Yeah.
What does the 3.5 represent again? That's
In this case, there's no physical meaning. It's like the expected value of roll of a die. Okay, so yeah, so in this case, so as I was saying, right? So everything depends on how you define the random variable. If my random variable had been defined as something more meaningful, like the number of times you have to toss to get a 4 or something, then you would get a different number. But here it's just the average outcome value of the die, which sometimes you may be interested in. But yeah, no, these things are not always interesting. All right, so that's some quick detour about random values and random variables and expectations. Okay, so for any random variable, you can define its expectation using that summation. Okay, and in our case, for now, we will use so x will be defined as the running time of our algorithms on array. So actually I will even have an x sub n. Okay, so it's the running time of an algorithm on array of size n. Alright, so is the definition of x sub n here. So this is a random variable, right? It depends on what choices the quicksort algorithm made. But what is the range of this of xn? Yeah. What is the range of the running time? I mean, clearly they're all integers, but can they be all integers? Can they be n cubed?
Depending on the output, depends.
Yeah, but I'm talking about the quicksort algorithm, right? So let's take quicksort with the pivot being picked randomly.
So from 0 to n power 2.
Yeah. So yeah, we've already argued that the running time is never more than n squared, right? Because we said that it ranges. I mean, even if it was very lopsided, you would still have only n squared. So this is a random variable that takes values. The range of this random variable is 1 through n squared. Maybe it will never actually be 1, but you know, 1 is maybe with probability 0. So now if I had to find the expected value of xn, So this is a messy computation, right? So what it's saying is, if I want to say that, if I want to do expected value of xn, if I use the definition I've laid out, it is sum over all I in z. In this case, I can sum from 1 to n squares. I times probability that xn equal to I. Okay, and this is a mess, right? Like, how do I, given some I, let's say I give you n to the 3 half or something, right? So that's an I in this range. And I ask you, what is the probability that the algorithm takes has a running time of I? This is something that you would expect would be a mess, because how are you going to calculate the probability that the running time is some time? So the trick is not to use this definition, but somehow use something something a bit more clever. Yeah.
Why would it start the range is 1 and its probability is 0?
Yeah, I'm going to start at the end.
Except that when you value that you're sure this probability is not 0.
Right. So there isn't, right? I mean, in the sense that you could say n, because then you start getting into how exactly this algorithm implemented and stuff, which I don't want to do. So yeah, so if you implement the algorithm in the way you normally do, then if everything is lucky, if you get a pre-sorted array or something, then your running time would just be, would be something like n log n if you always pick the middle guy. Okay, but yeah, we don't care about throwing in a few extra things, right? So in principle, I could have summed from minus infinity to infinity. Just to keep the sum finite, I'm doing it from 1 to n squared. Yeah, so usually you don't want to care too much about the range of a random variable, okay? Because you just want a rough bound. You just don't want sums that go off to. All right. So that's so this is clearly a bad thing to do, right? So this is something we don't know how to evaluate. So the trick we will do is to write a recurrence for this point. And these are what are called, sometimes people call them probabilistic recurrences. And the main idea is writing a recurrence for this expected value. Here. And this turns out to be something nice that you can do in this case. So how do you do this? Right? So we want to look at the quicksort algorithm, which we have here. It's a random to it. And we want to write an expectation for this, sorry, a recurrence for this expected value. Okay, so yeah, let's not let this slide repeat okay, so how do you come up with a recurrence for this? What is a recurrence for xn first? I mean, if somebody, let's say, these are my numbers, right? These are my AIs. And suppose I told you that in the first step, you picked the ith smallest element. Then can you write a recurrence for the expected time there onwards? Let me just explain the question a little bit more. Okay, so what I'm asking is, suppose when I have an array of size n, right? So in the initial call of the array, I split this thing into two subarrays. One of them is I minus 1, the other is n minus 5. Right? So this would happen when I picked the ith smallest element as my pivot. In this case, what is the expected value of expected running time of the recursive calls? Can you write an expression for this? Sorry?
Would be the running time, expect running time of the subproblem plus n.
Yeah, so in this case, you will have the expected running time of these two subproblems when you go to add up. So because you have to solve this subproblem, you have to solve that subproblem as well. So the expected running time would be, yeah, so that would be the sum of these two things plus this O of n term that you are using to divide. So in this, if I had picked the ith smallest, then I would have gotten the expected value of x n, sorry, I minus 1 plus expected value of plus 4. Okay. And this is if I had picked I as the pivot. Okay. And right. So now what is yeah. So how would you? What is the probability of picking I? So it's so the probability of each I of picking I equals 1. So what you can argue with now is that because of this, you can say that the expected running time on an instance of size n, okay, this is equal to sum over all i's. Okay, so this is the probability of picking the ith smallest kernel pivot times the probability that you have picked I, which is 1 by n, times the running time when you have picked 1 by n. Right? So this is plus 4. Okay, so choosing I happens with probability 1 by n. So maybe I should use different parentheses here. And if you have picked I, then this expression is the expected running time for everything that follows below, okay, for the recursive calls. And yeah, and the choice, and this I happens with probability 1 by n. So this is why you have this expression. Okay, so here I am using this previous definition of expectation and trying to write E of xn in terms of the previous terms. Okay. And what does I range from? I ranges from 1 to n. Here you can assume that it ranges from 1 to n minus 1 because you picked the last element that is. So yeah, if you would, for clarity, you can just keep this. Alright, so this is the idea. So you just have this can. So now you have something clean, right? So now you can now this is an expression that relates expected value of xn with expected values of things that are smaller than. And now you can do what you would normally do. You just define, let's say, yn or something to be expected value. And now this recurrence is essentially saying that y sub n equals sum over I to of 1 by n times y I minus 1 plus y minus I plus O of n. So I'll forget about the constants in O for now. I'll just write it as n because that doesn't matter. And so this is the recurrence that we get. Okay. So, but firstly is what we did here. Okay, so we essentially we are using the regular formula for expectation, but we are using it in an inductive way. So this is how you deal with recursive calls. Alright, and now you just have to solve this this recursive equation. So you have this yn equals sum over I1 to n 1 by n times y I1 and where you know that y0 equals 0. Y0 is like sorting something empty, it's 0. And this is what you've got to solve. And yeah, so I won't spend too much time on this. You can see that this can prove inductively, prove induction. That y let me just write yn less than equal to, let's say 2n log. Okay, and yeah, so the proof of this is, if you want I can do it, but I don't know if it is too well. It's just doing a calculation. Basically you just plug in, you want to prove this by induction, so you plug in I minus 1 times log I minus 1. Plug in these things as you would normally do, and you get. So do you want me to do this? Okay, so this is straightforward calculation. So, and it's not really important, but you can maybe there's a way of seeing this that is better. Actually doing. Yeah, I'll do one thing. I'll just do the simpler task of I'll try to evaluate what happens to one of these terms when you plug in this. So proof by induction. Proof works as follows. By plugging y I less than I times 2I into this. Right? So one of these terms would look something like y I minus 1 I plus n. This is I minus 1 times 1 n minus I plus n. Right? And this thing So if you use basically so if you use the fact that this guy is less than equal to log n, trying to see what you would get. So in this case, you would get something like I minus 1 times log n plus n minus I times log n. Because this would be less than equal to this. And this would be n minus 1. There are also factors of 2. This would be something like 2 times n minus 1 times log n plus n. I would like this to be less than equal to 2n log n. Is that true? This is probably not true. Okay, so I have to be a little bit more careful. Yeah, alright, so let's, yeah. Okay, so I can post this when I write the notes for this lecture. But this is a standard computation. You should be able to find this in many places. Okay, and yeah, so let's not spend too much time. Okay, so this, if you think about it a little bit, you'll realize that you can prove that yn is less than equal to 2n log n in that. Okay. So yeah, so approximating this by log n is too bad an approximation. So you have to be a little bit more careful. So if both were n by 2, for example, then you gain an extra n, which is okay, anyway. So let's not go into that. All right. So now the point I want to say is that in this case the expected value is only n log n. So of the running time. So now you should ask the question. So we know that what we have shown by this argument, by this recursive argument, is that the expected value of running time, okay, so this one is something like n log n, correct? So if I actually run it, what is the probability that I get a running time that is something like n log n? Okay. So is this clear? Right? Because how have we defined the expectation? Right? So the expectation was defined as sum over all I times probability that xn was equal to. Okay. So this is like saying geometrically you have some distribution. And it's in this case I goes from 1 to n. Okay, so this is 1, this is x. So there's some running time that goes like this, maybe it's oscillate, whatever, right? So it has some running time distribution that looks like this. Okay, so the y-axis is the probability, and this thing is the running time. So the running time goes from 1 through n squared. For each value, you have some probability associated. Okay, so this is how I'm plotting. And the question I'm asking is, what is the probability that your running time is more than something? So suppose, because this is the quantity that we really want to bound. Right? So you want to know, what is the probability that my running time is, let's say, n to the 3 halves? Correct? Because that would be a bad thing. Like it could be that your expectation is small, but with some reasonable probability you are having a really large running time. So does that make sense? Does the question make sense? So a priori it's not clear, right? So yeah, so I mean let's take a very simple example, right? So if you had a coin that is 0 with probability, let's say 99 by 100, and 1 with probability 1 by 100. So its expectation, if you compute it, will be 1 by 100. Okay? But in some sense, there is still some non-trivial probability that that the value is equal to 1. So there is still a 1 by 100 probability that this random variable has value equal to 1. So could something like that be happening here? Like in some sense, your probability of, your expectation is out here, but there is still some reasonable probability mass here. Okay, so this is n log n, and this is some bad running time. Okay, so let's say I'm unhappy if my running time is more than 1000 times n1. Then maybe I feel that okay, this quicksort is not really good, right? So then maybe I would like to do more sorts. So yeah, so can you bound the probability that your running time is, let's say, more than 1000 n log n? Right, so is the question clear? Yeah.
Know that the total probability is 1. First. So if you take the integral on the range that you're interested in, you can figure out what proportion of the probability is less than that.
Okay, so what he's saying is, look at this formula, right? And so here you're summing probability going from sum of I going from 1 through n square of I times this probability. If a lot of probability mass was here, okay, which means the sum of these probabilities on this right part was very high, somehow it can't happen that the expectation is so small. Okay, so that's what we want to intuitively show, right? Because overall the sum of all the probabilities is equal to 1. Okay, so if I count the height here, and so on, these heights add up to 1. Okay, so if my expectation is something which is pretty low, you can't have too much of the summation coming from things that are much larger than 1000. Okay, so that's the general idea behind what we would like to show. Okay, and yeah, so let me just quickly try to prove this. Okay, so what I want to claim is that if the expectation is n log n, then the probability that xn is more than 1000 times n log n is less than or equal to 1 by 1. So this is a simple claim that I want to show. Okay, so I want to show that the probability that you are more than 1000 times your expected value is less than 1 by 1. Okay, so that's like saying, okay, maybe you will fail, but your failure probability is very small. So this is what I would like to argue, and this is a more general theorem. So this is called Markov's inequality. Okay, so what it says is, morally, it says that if x is a non-negative random variable, that just means it never takes negative values. So non-negative random variable, then probability that x is more than some constant times the expectation is less than or equal to 1 divided by that In the previous case, I was setting C equals 1000. So this is Markov inequality. Morally, it says that a random variable cannot be much higher than its expectation too often. And this you would intuitively expect, right? Because it's a non-negative random variable. So yeah. Okay, so let's see how you would prove this. Okay, so let's draw out the distribution of x. Before, so this is 0 goes on to infinity. So this is the probability. Okay, and let's call this the expected velocity. So now the proof is actually very simple. Okay, so suppose not. So suppose this probability is more than 1 by c. Okay, so the probability that x is more than c times e x is more than 1 by c. So that means I have more than 1 by c mass on this side. Okay. Now let's get a contradiction to the expected value. Okay, so we know that expected value of x equals sum over all I bigger than or equal to 0 of I times probability that x is equal to 1. So I can break this sum up into sum over from I going from 1 to the expected value of x of I times probability that x equals to I plus sum over I bigger than expected value of I times probability. Okay, sorry, I want to do it with the C times. X equals 9. So I want to break this sum up into things up to c times e of x and the integers beyond. Okay. And right, so now I use a very simple inequalities here. And so what I want to say is that this term, because it's a non-negative random variable, this is clearly non-negative. Right? So this is always bigger than x. Now, what do I know about this term? Okay, let's consider a second term. Consider the term sum over I bigger than c times e of x, I times probability of x equals 9. So I want to say that this is definitely bigger than sum over I, the same thing, c e to e of x, of c e x times probability that x equals. Because I is always, this in the summation, I is always bigger than c times e. So this is trivially true. So now I can take this term outside, and this is just c expected value of x times. Now what is sum over this thing of the probability of x equals 9? So I want to say that this is just equal to the probability that x is more than c. Okay, because I mean I'm just this is the definition, right? So x only takes integer values. If I sum over everything more than this is the correct. And I have assumed that this probability is more than 1 by c. Okay, so that is what we are saying. Suppose if possible this would. And so then this would be strictly bigger than expected value. And this is a contradiction because you started with an expression for expected value of x, and you have something non-negative plus this term. This term is already bigger than expected value. Okay, so this is a contradiction. Okay, so this is why your probability cannot be more than 1 by c. So this is a very general statement which shows that the probability of a random variable being more than its expectation by a factor is less than equal to 1 divided by. So let's stop.